A giant of the sea roams the ocean, a huge ship with a massive crane. This is the Oleg Strashnov, one of the biggest monohull crane ships in the world. Its mighty boom is able to lift up 5,000 tons of weight. It is not only a huge crane, but also an efficient multitasker, integrated into a ship system that stays stable in the water, whatever the weight, whatever the elevation. This is a true marine monster, a legend of the sea. The sun rises over the Dutch port of Schiedam, located on the busiest waterway of the country, west of Rotterdam and close to the open North Sea. This is where a hub of nautical companies provides the most advanced engineering support for the whole of the maritime industry. Gusto MSC is one of the oldest offshore design and engineering companies of the country, and it is where the world's largest and most advanced nautical cranes are built and integrated into ships that are also designed here. The glass and steel interior of the headquarters has been grafted on a building that was once home to the company's competitor when it was founded a century and a half ago.
We see the ship and the jackup, but together with what we call the mission equipment, like cranes, we see that as an integrated design, which basically the purpose of this type of ship is not so much sailing, and the purpose of the ship is to perform a heavy lift.
That's where it starts with. Is it for a ship, or is it for a jackup or a semi? That already has a big impact on the type of crane and for the design.
The name of Gusto MSC is intimately tied to the world of shipborne cranes, machines that have played a fundamental role in the offshore energy industry for decades. Little-known machines that have been strategic for the growth first oil and then the wind farm businesses. Gusto MSC's clients are companies that, amongst other things, require heavy lift capacity offshore. The cranes that the company has designed are integrated into ships, jackups, and rigs that not only navigate the seas but also have necessary stability to withstand the environmental forces and perform their heavy lifting tasks. Arjovan Putin is the chief engineer of the crane department at Gusto MSC. He has honed his skills on designing massive cranes of all types, including the huge 5,000-ton crane of the Oleg Strashnov installation ship.
Lifting capacity is one of the most important things, and the outreach, in fact the combination. So for example, if it is 5,000 ton at 30 meters or 40 meters, that's really a big difference. Once we know that, then it is important also to know the lifting height, especially nowadays for the wind turbine installation cranes. Then the required lifting height increases quite a lot. So that's also an important factor, and it can also have an impact on the complete design, what we are going to use.
Alain Vassink is the marine architect who designed the Oleg Strashnov and is now sales director for the Gusto MSC cranes.
Gusto MSC is a design and engineering firm, and we specialize in design of mobile offshore units of all sorts and types, from jackups to semis to ships. The company started out as a shipyard already in 1862 and has made a lot of different things in the time, but it has pretty quickly specialized in heavy-duty workships. Floating cranes already started in the 1900s, and dredgers and other ships. And especially from the 60s to the 70s, it started to specialize in the offshore industry.
We have a couple of main components in the crane. So that's the foundation of the crane. Then you have what we call the slewing platform. So everything is mounted, everything that rotates with the crane is mounted on the slewing platform. Then we have the boom itself, and we have the A-frame. In most of the cases, can be a tower as well. And all the ropes are going through via the A-frame to the boom. And it depends on the loads on those main components. So we have an in-house developed program, software, which we use to determine the loads on those main components.
The massive crane that Alain and Arjo have built is the result of 7 years of hard work, first designing and then building and testing the ship and crane.
It was in the spring 2007 that we got the order for the delivery of the crane. Then we spent about a year on the whole design, and then of course already we start purchasing materials because there are some long lead items. Especially in that time the market was booming, so delivery times increased quite fast. So we ordered all the long lead items as soon as possible. Then the eventual delivery was almost 4 years after we had the original order.
Yeah, so we started out already in 2005 with the owner, CWF Lifting, to come up with a concept for a fast crane vessel. Most of the vessels are quite slow, 4 to 6 knots at that time. Fast crane vessel, versatile, with the then highest lifting capacity for monohull in the world. And they wanted to have a design that could sail fast and be very stable when doing lifting operations, which usually is a contradiction.
While Gusto MSC actually builds the cranes itself, ordering in the parts from outside, the company provides the ship designs to third parties who construct the ship. The two key elements of the integrated ship and crane system grew by the day until the ship was ready for launch. It was the 22nd of August, 2009.
I've been involved since the inception of the ship. Seeing it enter the water was quite an exciting moment. It's for me as a naval architect, that's the birth of the ship.
This is the Oleg Strashnov. The massive ship is 183 meters long, 47 meters wide, and has a draft of 13.5 meters when working. However, when sailing, the ship has a reduced draft of 8.5 meters and reduced beam to give it greater speed than any of its competitors. Oleg Strashnov is one of the largest monohull crane ships in the world, and the original owners had some specific and very ambitious requirements for the ship. Indeed, it was and remains a revolutionary ship in many ways. It is one of the fastest of its class. It has one of the largest cranes, and above all, it offers an amazing amount of versatility. It is truly a marine monster to be respected.
So the ship came out at a little over 180 meters in length, with two beams, of course. So we have 37.8 meters on the low draft, and we've got 47 meters on the deep draft. And to make this happen, you need quite a high ship, because you have to still have some freeboard when you're in your deep draft. So you're at around 18.2 meters in depth of the hull, with ultimately a displacement of around 70,000 tons at the deep draft.
The marine architects of Gusto MSC accepted the challenge to design a ship that was highly unconventional, but also highly competitive in terms of speed and, of course, fuel consumption. The design criteria for the Oleg Strashnov included the ability to work on site, while the ship also provided a stable base for the massive crane with its unique revolving main hook, with a 5,000-ton lifting capacity. Designing such a ship maintaining balance when the crane arm is fully extended was a challenge.
We developed a very special hull shape with them, which is a patented hull, which has a dual draft, where you can have a small draft, where you have a narrow hull, so less resistance, which is quicker, less fuel consumption, but less stable. And when you do a heavy lift, you need a lot of stability, but no speed. So you can go to a deeper draft, and then the ship is much wider and has more stability.
Main characteristic is that it can lift 5,000 tons. It does it at an outreach of 32 meters. The maximum overturning moment is at another distance. That's 3,800 tons at 43 meters. The lifting height is approximately 100 meters above the main deck for the main hoist. And there's also an auxiliary hoist, which can lift about 30 meters higher. That has an 800 tons capacity.
Oleg Strashnov, however, not only had to have one of the biggest cranes on the high seas, but also the widest range of lifting capacity. So Arjo introduced a unique design into the crane, a crane within a crane.
There is a trolley hoist with a lifting capacity of 30 tons. It can travel along the boom and it can lift 30 tons. But yeah, we didn't want to just add steel to integrate that. So what we did, we made in fact a fifth cord boom. So there's a fifth cord in the middle, and we create so we have 5 cords who really transmit the whole load. So that's a bit special. And yeah, in that way we could design quite a light boom, even with this integrated trolley hoist. If you use the trolley, you can keep the boom at the same angle, and the trolley just moves along the boom. So you don't have to move that slow boom, you can just use the trolley. That works quite fast.
Once the design phase was over, the ship and crane could be constructed. The day came when this monster had to be built, and Arjo and Alain worked together to deliver one of the most amazing and least celebrated ships plowing the ocean waves. In particular, the lifting part of the unit required some of the most innovative construction techniques. Everything is massive.
The boom cords, for example, so the big tubes are made from 690 material. That's steel with a strength of 690 megapascal. And also other parts like in the A-frame, the backside, mostly parts in tension, are made out of the 690 yield material. But for example, the braces, which are welded, the tubes in between the big cords, are made of 355 yield material, because they are not governed by the stress in the material, but by vortex shedding.
However, most of the crane's work is done with small loads, and this is where the supplementary lifting machines come into play.
Well, a special thing about this crane is that, normally when the crane is rotating with an empty hook, with a boom at about 60 degrees angle, the CUG is exactly in the middle. That was one of the design criteria. There is a removable ballast system at the backside of the crane, and by doing this, then most of the operations are actually small loads. So the lifting capacity is 5,000 tons, but I think, more than 90% of the lifts is less than 100 tons. And during all those operations, the boom is at approximately 60 degrees, and it can rotate without having to ballast, because the center of gravity is in the slewing center.
The industry sets standards, but these cranes are so huge that extra safety measures have to be introduced to make sure nothing, absolutely nothing, goes wrong. There are several main component parts of a crane. The boom, the long arm that extends out to sea to lift heavy loads, and of course, the A-frame that controls the extension of the boom, lifting and lowering it as necessary, and through which the lifting cables pass. There is also the ring platform around which the crane swivels, and the motor that provides the power both for moving the crane and turning the winches that pull the loads up or down. On Oleg Strashnov, all these components are massive. Oleg Strashnov's A-frame is also special, as the client required the ship to pass under the world's bridges, such as the Bosphorus Bridge that joins Europe with Asia, so as to engage in offshore heavy lift in the Black Sea, one of the world's most strategic areas for energy resources.
We added an extra hinge at the aft side of the A-frame, so at the back leg, which is a vertical leg. Normally that leg is in tension, but during transit of the vessel there can be a vertical load downwards as well, and then it's in compression. What we did is we created an extra hinge, which is normally locked by a small beam, and when we want to lower it, first the boom is lowered into the boom rest, and if we keep on rotating with the boom hoist winch, then the rope tension is lowered, and eventually the A-frame should go backwards, but you have to help it a bit. So what we did is there is a locking system, and when you unlock it, there is a hydraulic cylinder, and it gives us what we say a kick in the knee, so it starts to bend, and then on its own weight, it has to go backward.
Once these major design features were established and construction completed, the actual assembly of the massive crane began. This in itself was a mega-lift operation. The motor housing was built in China and delivered to the Schiedam docks, where it was to be integrated with the ship. Here it was lifted onto a massive barge and lifted by two shear legs to be transported to Oleg Strashnov. The motor housing had to be positioned with millimetric precision, and only the expert eyes of the designers and construction workers could guide it properly into place. It was placed delicately on the base and the pin. The bogies followed and were fitted perfectly on the rails, allowing smooth rotation of the crane. Then the A-frame had to be fitted. Not only the static part had to be precisely connected with the crane base, but the folding segment had to be lowered so that the massive pins that allowed it to be collapsed to reduce height could be inserted accurately. This in itself was a mammoth task, and yet there was much work still to be done. The largest single element of the crane was now ready to be moved. The heavy lift company, Sarens of Rotterdam, moved the boom onto a barge using self-propelled mechanized transports, or SPMTs, from which a massive shear leg was able to lift the 100-meter-long steel trellis structure onto the huge hinges that awaited it on the crane body. This was the crucial moment of the assembly of the whole Oleg Strashnov crane ship. This was followed by lifting the ballast for the crane, the counterweights that are brought into play every time the boom lifts a weight at the fullest extension. The next stage involved the reeling of the cables and ropes. Dozens of steel cables were pulled through the boom guides and then meticulously wrapped around the winches. The closer to the core of the winch, the less cable is released, so the automatic gears are key to keeping lifting speed uniform. The 64mm cables had to be guided by special ropes through the boom all the way to their winches, one by one, and wound on accurately, securely. This is the heart of the whole crane, where the lifting actually takes place.
Yeah, from the client we receive certain lifting speeds. So they specify a lifting speed, an average speed, because if you have the winch, there are several layers of steel wire rope on the winch, and so the rope speed is different when you are at the, let's say, the 10th layer or the first layer. So they specify an average speed, so that's where we are working with. We calculate the required power.
Now that the crane had been constructed and installed on Oleg Strashnov, the next crucial stage could begin. Oleg Strashnov is the largest monohull crane ship in the world and flaunts three very special characteristics that other ships of the same type do not enjoy. It's fast, its crane can lift 5,000 tons, and it is incredibly versatile. On the 11th of March of 2011, the ship was ready to be tested. The crane capacity was the first requirement that had to be tested. The trolley crane was put to the test. This was done by filling balloon-shaped containers with seawater and simply lifting. Once these tests had been completed successfully, the onboard computer system could be calibrated, providing accurate load readings. The next test phase involved putting the secondary hook through its paces. Now came the moment for testing and calibrating the 5,000-ton crane. To do this, the crew filled a whole barge with water, and the main hook was lowered to lift it. Not only did it have to lift the weight of the barge and water, but, just for good measure, an extra 500 tons. The crane successfully lifted it and swiveled with it to put the structure to the test at all angles. The crane passed the test with flying colors. The ship was now ready for sea testing. So let's take a tour of the Oleg Strashnov as it is today. These photographs allow us to see the inner workings of the offshore workhorse. This is the view from the crane driver's seat. The whole length of the ship is now visible, with the hundreds of pieces of auxiliary equipment on it.
From the crane side, it's you have lifting tools, all kinds of tools that you use to actually pick up the load, rotate the load, control the load, to put it into, once you put, for instance, for a wind turbine, you put the monopile on the seabed, you need to keep it in place, otherwise it falls over. So there's a gripper that keeps it in place. Then you need a big hammer that is actually lifted on, and that's also a couple of 100 tons, the hammer alone. And that is all the equipment for the lifting operation itself. Then for the positioning you need the ROVs, so the remote controlled robots underwater. Surface diving is still used. It's amazing how much equipment fills up the deck when you do such an operation.
The main hook was specially forged as a single block just for this crane.
The crane is electric powered, so it receives power from the vessel. The vessel has generators, and we receive 6.6 kilovolts from the vessel. It's about 6,500 kilowatts is the power that we maximum consume. And in the crane at the backside there's 3 levels of electrical equipment, and there it is transformed to 690 volts. And we have rectifiers. They make from the AC, they make DC, and then we have drives who convert that power to the motors at a certain frequency and speed.
Special safety features ensure that accidents with the winches are practically impossible, including clamps on the cables, sensors that stop the hooks from impacting the top of the crane. The crane is also designed to be able to operate in harsher weather conditions than its competitors.
Then the hook is hoisted towards the boom. We always know the exact height of the hook, and when it's coming close to the boom, there is a warning. When it comes a bit higher, it automatically stops and there is an alarm. And when there is the warning, it already goes to a lower speed. When there is a situation that the crane operator wants to go even higher than that, he can overrule that, and there is another safety switch at the boom which stops that motion, and that cannot be overruled anymore. And that's the whole crane. Everything is safeguarded by at least two systems. If one fails, then the other one still is there as a backup.
The boom and hook are not the only areas of the ship that can go wrong. There is a double braking system on the cables, and winches too that can hold loads in place if there is a danger, or even lower them slowly if power is lost.
These winches have a double brake system. You have a system on the drum itself. That's for a holding brake and for emergency. And there is also a brake at the gearbox. So there is the motor that transfers the load to a gearbox. And so that's the high speed. And then one of the intermediate shafts is used to mount the brake. And there was a bit of a special request in this case, because we also needed to do emergency lowering on those brakes. So in case there is no power available, we need to be able to lower with the brakes the load.
Oleg Strashnov has a class 3 dynamic positioning system, which means that it can stay in location with movable thrusters, but it can stay in location even after a fire in one of the engine rooms. So it's got redundant engine rooms, redundant thruster rooms. A total installed power is needed of 27 megawatt, divided over 6 generators, 6,6 kilovolt high voltage distribution system, which is top end for this type of vessels.
Keeping the ship stable and perfectly positioned to accurately lay the foundations of oil rigs or wind turbines in extreme weather conditions is an essential requirement for a supply ship like Oleg Strashnov.
There's a lot of positioning equipment. It's not only GPS, they also use pre-located sensors that are put in the field to get the exact right location. That is for wind turbines, but that's also when you're installing big jackets for offshore oil and gas. That needs to be pretty precise. And there's a lot of specialized equipment used. GPS is only one of them.
Keeping the ship on site is done by anchors attached to cables that can be pulled to move the ship one way or the other.
In addition, what we included was a mooring system, an 8-point mooring system, which is also used a lot. These are 8 big mooring winches on the 4 corners of the ship, and each winch with a 15-ton anchor. So we are able to keep her in position in quite heavy conditions.
The same is true for crane movement, as every change in the ship's center of gravity has to be compensated for.
When we do have a big load, indeed the vessel needs to ballast. So there is a ballasting system, and it pumps a lot of water from one side to the other side. So for example, when we do a test load with 5,500 tons, to make 1 revolution, we do it very, very slowly, because the crane can do it in 3 minutes, but the vessel needs to pump a lot of water to the other side all the time. So 1 revolution takes then about 1 hour instead of 3 minutes.
The ballast system on the crane vessel is one of the key systems that you have on board, because you have to keep the ship upright and you have to compensate for the crane. So the crane is revolving and the ballast system has to compensate for all the loads that act on the hull, and it's a ship, so it moves. And in this case, with this kind of crane, with a large outreach, you need a lot of ballast capacity. So the ship has around 50,000 cubic meters of ballast capacity, and it has a pumping capacity of 20,000 cubic meters per hour.
The true power of the crane lies in the motors that power the winches. They are 6,000 kilowatt engines and have redundant backup systems just in case they fail and a heavy load has to be brought down gently. This is the heart of the crane system. The cables operate 4 different cranes positioned along the boom: the smaller 30-ton crane and the massive 5,000-tonner. This is the huge ring built to allow the bogies to swivel the crane. This too is powered by the electric motor, which is supplied by the ship's generators. The crane could not operate without the ship. This is the engine room, where the engines can push the ship up to 40 knots, as fast as many of the cruise ships that plow the seas today. The expansive deck has a capacity of 10 tons per square meter and covers an area of 3,500 square meters. At last, Oleg Strashnov was ready for operations. Its extreme versatility allows the ship to perform all the operations involved in building an oil rig or a wind farm. This animation shows the phases of laying the foundations of a wind farm control center. First lifting the foundations and positioning them on the sea floor, and then moving the structure itself, using the 2 hooks on the crane to right the steel structure and position it onto the foundations. The really heavy lift comes with the upper platform, a monoblock of drilling and living areas, all less than 5,000 tons. The ship's versatility allows for it to carry out many operations, and this in turn reduces time on site, generating significant savings for oil companies and wind farm builders. The whole new source of energy is developing all around the world, and this ship has the ability to supply the wind turbine market optimally. Offshore wind farms maximize efficiency and can be bigger than those built on land. The size of the individual wind turbines that must be installed on the seabed is also growing.
It was designed to do operations for the oil and gas business. But the first job it had after it was finished was the installation of monopiles for quite a big wind farm. And they were very successful at that, at CV Heavy Lifting. And afterwards, the majority of all the work they have done with the vessel is for installation of foundations for wind turbines. They also did some interesting oil and gas jobs, but the market changed quite a lot in that period.
In these images, we see the phases of wind turbine construction and how the massive 5,000-ton crane is suited to the task. The ship is able to lay both the foundation and the mast, and then the turbine itself, all in sequence.
When we designed Oleg Strashnov, we were looking at offshore oil and gas, and then you do a heavy lift, and that is one project, one heavy lift. In offshore wind, every day you do a heavy lift. It's like an industrial process. And that means that you have to be highly efficient in doing the lifts. And Oleg Strashnov is one of the vessels that have been very efficient in that. And that is mainly, of course, the operator. See, we have a lifting that has been doing that, but we are a bit proud of that ourselves as well.
The Oleg Strashnov sails off onto another assignment as the offices of Gusto MSC and the port of Schiedam are closed for the night. There is no shortage of work for these new versatile crane ships. The future for seaborne heavy lift has never looked brighter. Another day at the port of Schiedam, Netherlands, the heartland of the nautical industry, a hub for nautical services worldwide. This is where Gusto MSC enables and supports safe and efficient operations at sea. The Oleg Strashnov crane ship has inspired other vessels, including the Hiyang Shigyu 201, which was built in China based on Gusto MSC design, and also mounts a 4,000 metric ton capacity crane and a pipe laying system able to lay rigid pipelines in 2,000 meters of water. In the energy business, monohull ships are not the only solution, however. So the company has designed several jack-up rigs that are more stable than ships when working at sea.
There's a clear difference in foundation installation and turbine installation, where especially the foundations are getting bigger and heavier, but they can be installed by ships, which are usually can be easier built with larger cranes, while a jack-up is more stable, less movement especially, and is very well suited for turbine installation because of the fragile parts.
When we delivered the vessels and the cranes for wind turbine installation, the size of the wind turbines was for 3.5 megawatt till 5 megawatt. At the moment it's 8 till 9.5 megawatt, and the expectation is that will grow in the first, let's say, 5 years until 15 megawatt, and beyond that probably even to 20 megawatt. So there is more or less no crane capacity available in the world to install that.
Rather than just design another very big crane, we looked at, okay, how can we make a smart solution that also better fits the jack-up, because otherwise the boom starts to stick out 30, 40 meters, which is highly impractical. So we explored the telescopic boom crane, and of course they exist in land cranes, but also that's a capacity that's nowhere near what we're doing here, because we're talking 1,200 tons plus capacities. So we developed a new system for this telescopic crane, and that's what we're proposing to industry now for this next generation of turbines.
And we have focused mainly on the telescopic crane, which can be retracted. Then it can lift quite heavy foundations, but you don't need the high lifting height. And in extended mode, it can also lift the turbines and the blades, and then the load is lower, but it's still about 1,200 tons. But you need a lifting height of something like 160 meters above vessel deck, so that's really, really high. We have a truss boom, and what we do, we extend it using a reeving system, and when it is extended, we have pins which connect the extendable part with the base boom.
The company also supplies smaller cranes for oil rigs, as well as a unique hydraulic jack-up system that is currently used on oil prospecting rigs the world over. The company is growing in the Far East market, and the Fu Shuan Sang Sha Mani jack-up oil exploration barge has a 1,000-ton capacity crane. However, Gusto MSC is also working on a new division of versatile cranes that may change the face of heavy lift for decades to come. One of the jewels in the crown of Gusto MSC is this mini crane built to be mounted on the leg of the rig to provide especially fine lift. Named after a crab's claw for its crab-like grabbing motion, the Chila can reach below the cantilever and elevate toward the main deck, providing crane access to areas that were traditionally blocked by the drilling cantilever. By being able to work in this area, Chile has significantly reduced total well construction time. And in the energy sector, time is money. This crane, with its multifunctional claw arm, is also special because it can easily be taken apart and remounted and retrofitted for different jobs. But it also is making repair work on platforms out at sea safer for workers by literally lending a hand in narrow, small spaces. By separating wireline operations from the drill floor operations, Chile effectively reduces human interaction between the different crews doing different jobs.
We have also put a lot of effort into what we call the round-the-leg cranes. They are specifically developed for the jackups because you have the 4 legs that are sticking out, and you want to be able to have as much freedom with the crane as possible. So the logical thing is to put it around the leg, which had been done before, but nowhere near the capacity that we were doing. So that was really a first off that we did for our round-the-leg cranes around the late 2000s. Of 800-ton capacity.
The wind blows constantly across the dunes of the Netherlands' northwest coastline. Just offshore, wind turbines are being laid to create some of the largest offshore wind farms in the world. The Dutch are world leaders in this sector, and Oleg Strashnov is poised to capitalize on this rapidly expanding new market. As demand for energy continues to surge, oil exploration will continue in the petroleum-rich North Sea, and dependence on renewable wind energy is also likely to expand, creating many new opportunities for these kinds of versatile marine cranes. The sun sets on the port of Schiedam, the heart of heavy lift in the Netherlands. This is where ships have been built for centuries. This is where cargo has been handled by traders in the great Dutch tradition for centuries. Nowhere is more suited to the development and construction of some of the world's most clever cranes.